Okay, so yeah, for people on Zoom, I hope you can hear me. Thumbs up if you can hear, like, feel free to type in chat if you can't hear me. And yeah, I'll try to keep an eye on the questions on chat, but no guarantees to be in real time. Alright, so I just want to go back to last week's tutorial quickly for question 6. I think there's getting a lot of emails about that because the solution the first slide is a bit simplified compared to what you'd normally expect in a real situation. So it might look a bit odd. So question 6 was asking, compute the root mean square velocity for oxygen at both 300 Kelvin and 1000 Kelvin. Okay, so you probably just went ahead and did a ARMS is just equal to the average velocity. Oh, sorry, average velocity square root. And then you can get this from your average kinetic energy, so going from average half mv squared. And with amplification theorem, you can get this as the degrees of freedom divided by 2 times Boltzmann's constant times the temperature. So I think this is where it was a bit like sketchy. So in the, I don't think, see if they can actually see the board. You have to move this closer. Slightly better. Yeah, so normally with F in the solutions, we just assume it to be 3 because it's 3 translational degrees of freedom. Makes it easy just going in 3 spatial directions. But for oxygen, because of the diatomic molecule, O2, so you can actually have rotations in these like 2 directions. You can't rotate along this axis because the quantum nature won't let you, because if you spin along this axis, then you can't tell because you're not supposed to be able to tell point particle spinning. So you only get 2 additional degrees of rotational degrees of freedom. So the real answer will be subbing in F equals 5 for this question, and then you should be able to get a slightly different answer, but just out by a factor of 2. So I think VRMS for 300 Kelvin, if you plug in 5 degrees of freedom, you should get a different answer to the one I put in the solution. It should be 625.1 meters per second. And yeah, you can also sub in for 1,000. For 1,000, it's still 5 degrees of freedom. So I think it will be more interesting if it asks for 10,000. At 10,000, then you excite 2 additional degrees of freedom from vibrational. So if the question was asking 10,000, then you would sub in F equals 7 for your VRMS at 10,000 Kelvin. So that might have made it more interesting. But yeah, at the end of the day, in the exam, if they ask you this, they're going to tell you how many degrees of freedom you have, or they're going to provide you with like a plot. Usually the plot looks like your temperature in kelvins here, and here's your number of degrees of freedom, and it will look something like this. So like here's probably like, I don't know, 200 Kelvin. So at 300 you'll have 5 degrees of freedom, here's 3, and up here's 7, and like 10,000 is around about here. So you probably get given something like this, and you're just going to learn to read off it and at the particular temperature and take the one that you need. But like a factor of 2 and the story problem is not that big of a deal. Okay, any questions? All good? Any questions on Zoom? No? I think the rest of the tutorial one is pretty boring. We should be able to do all of them, and good to save them for practice later if you study for exams. Okay, so for this week, starting from question 1. So you have an ideal gas expands from V1 to V2 isothermally. So T is constant in this case. And you want to write an expression for the work performed by this gas against an external load that varies. So the system is always in equilibrium. So if the system is always in equilibrium, that means you can draw it out on a PV diagram. So it goes like that, going from somewhere V1 to V2. And you want to figure out the work. So remember, work formula is just dW equals PdV. And once you pick out a particular equilibrium path, you can just say, okay, work from going from 1 to 2 is equal to the integral of P dV from V1 to V2. And it's an ideal gas. So here we know P is going to be a function of the volume, and we can use the ideal gas law to find out what this function is. So P is equal to nRT on V. So we simply sub this into here, and we get V1.
And it goes like.
No, okay. All right, so nRT is a constant, so N and R are definitely constants, and T here is an isothermal process, so that can come up front. And you get 1 over V dV, and that's just a trivial integral. So you get nRT log of V2 on V1. And since it's an isothermal expansion, so V2 is larger than V1, so this is going to be a number larger than 1, so this whole thing is larger than 0. So you're doing positive work. So work is done on the gas. People finish copying down. Are we going to move on? Let's leave here for another 20 seconds. It's done. You've been expanded, so it's done by the gas. Yeah, because the gas is pushing outwards. Okay. So question 2, very similar. You get an ideal gas expanding from V1 to V2 adiabatically. 2, V. Looks about the same, except it's now like a adiabat instead of isotherm. V2. Derive an expression for the work performed by this gas against an external load. What data would you require to evaluate and determine a constant result? So same thing, use figure out the work by doing PdV. So W from 1 to 2 is equal to V1 to V2 PdV. Except now it's an adiabatic process, so you have to use PV gamma is equal to some constant C. And here you sub in that P is equal to a constant divided by V and gamma, and putting that into this equation, integral. So you get C is equal to integral, work is equal to C times the integral of V1 to V2 of 1 over V to the gamma dV. And that's technically a very simple integral, so you just get 1 over V to the gamma minus 1 times 1 over gamma minus 1, going from V1 to V2. Wait, no, sorry. That's 1 over 1 minus gamma to V to the 1 minus gamma. My bad. Okay, so then now you can sub it in. So C over 1 minus gamma times by V2 1 minus gamma minus V1 1 minus gamma, like that. But in this current form, it's not quite useful because you don't know what this constant is and you don't know what the gamma is. So you want to reduce it to at least just one variable. So you can get rid of this constant by going back to this relation again. So you can see that P is equal to C
on V on gamma. And this applies to both 1 and 2. So every point on the adiabatic, this is satisfied. So you can take out a factor of, put this C back in and then take out a V on gamma, V2 to power gamma in here. So you get 1 over 1 minus gamma, V2, so that's the 1 power here, and then times by C divided by V2 to the gamma. So you're basically breaking this apart. And you now know this is equal to P2. And same thing for V1, so you get V1 times C divided by V1 to the gamma. So now you got P2 and P1 in here. So now you can just get 1 minus gamma, P2 V2 minus P1 V1. And now you know all the state variables, so you just have to figure out gamma. That's all you need to figure out the amount of work that's done. So that's a lot easier than having to find the constant.
We just submit PV the gamma again. So, like, if we didn't degree of freedom.
Oh yeah, you could. And in this case, since V2 is larger than V1, so this is positive. All good so far. This is within lecture materials. Okay. No questions from the online people? No. Like I have enough room to do the efficiency questions. I've got one board here. Okay, so question 3. The temperature of an ideal gas at an initial pressure P1 and volume V1 is increased at constant volume until pressure is doubled. So yeah, first draw the PV diagram for this. So you're starting somewhere and then you want to double the pressure. So let's just call this as 0.1. So you got V1, P1. And you increase it until pressure is double, so you go up a bit. Here where you still have V1, but you go P2. And P2 is equal to 2 times P1. And then the gas is then isothermally expanded until pressure drops to its initial value. So it goes down this way until it goes back to P1, but at some V3. 1, 2, 3. And then it's compressed at constant pressure until volume returns to the initial value. So it returns back this way. So your cycle goes like that. And this is an isotherm. Okay, so that's part 1, sketch the process. Exactly. Hopefully. Okay, and part 2, computer work in each process. And the net work done by the cycle of n equals 2 kilomoles. I guess there's some data over here. So n equals 2 kilomoles. And P1 equals 1 atmosphere. And V1 is equal to 4 meter cubed. Okay, so to find work, is always just do dW equals P dV. So then for the first process, work going from 1 to 2, you do no work because your volume is not changing. So you stay in a constant volume, so dV is 0, so this whole thing, you don't have to worry about it. So now let's just move to the isothermal part. So this is exactly the same question 1, so you get work from 2 to 3 is equal to nRT integral of dV on V from V1 to V3. It's not V2 here because V1 is equal to V2, but if you label it V2, just remind yourself to sub it in later. So it's the same thing. There you get nRT log of V3 of V1. So that's a work done in isotherm, right? Oh, you can, V1 is equal to V2, so it doesn't really matter yet. So you can sub it in later or sub it in now, it's the same. Okay, so the last one is the work from 3 to 1. So this one is really simple because in this case, your pressure is constant. So PdV, when you integrate, the P comes out the front. So you just get P times integral of dV from V3 back to V1. So that's just P of V1 minus V3, like that. Yeah. Okay, so to find the total work, you just sum all of them together. So the work over the entire cycle, the sum of all of the work. So you get nRT log of V3 on V1. So this one's positive, so you can just leave it as it is. But this one, since V3 is larger than V1, so this will actually give you a negative work. So make it clearer, just rather than adding this, just subtract P V3 minus V1 to avoid any confusions. Because you know this is going to be negative, so just swap it anyway. Okay. Yeah. Now you can just put it back in, except you don't have to actually. I don't know why they gave you little m, because this is not necessary, because you can work out what nRT is. Now, on the isotherm, nRT is equal to pick a point, either P2, 0.2 or 0.3, so P2, V2, let's say. So this you can work out already, because P2 is double P1, and V2 is the same as V1. So this is just 2 times P1, V1. And those two are given to you with numbers. So you don't have to worry about something in the nRT at all. You can just put this back into there, and that gives you the numerical answer. So your work over the entire cycle is given to you by 2 times P1 V1 log of V3 on V1 minus P, which P is that? That was P1. This is P1. V3 minus V1. Except V3, we have to figure out what I do here. Oh yeah, sorry. So to find V3, you also use the isotherm. So the isotherm applies to this point and at this point. So you have nRT is equal to P2 V2, also equal to P1 V3, or P3 V3 to make it a bit clearer in the labeling. And then you get, okay, this is 2 P1 V1, and P3 is the same as P1, and V3 is here. So you can cancel out these two pressures, and you get V3 is equal to 2 times V1. So you can put that into here. So rather than V3, you get 2 times V1. And then put in the data. So P1 is equal to 1 atmosphere, but you need it in SI units. So P1 is 101.329 pascals. And yeah, V1 is already in SI, so 4 meters cubed. And just sub it into here. Once you put in a calculator, you should get 156,572 joules. All good? Any part? Not clear? Oh, okay. Oh, if you got the same like equation at the end, I think that's fine.
what's different?
Yeah, that used to be V3. Yeah. Okay, if everyone's happy with that, then we'll move on to question 4. Okay, question 4, you get given this PV diagram. We have 4 state points, so you got A down here, B, C, and D. Don't ask me why they labeled in that order. And you can connect all of them together and plus 1 curve through in the middle. Okay, and it tells you that along the path ACB, so going this way, you get 80 joules in here, so the path ACB. You get 80 joules of heat going into the system. And your system does 30 joules of work. And now the question is, how much heat flows in the system along the path ADB if you go this way instead? So, okay, the important part here is to work out the change in internal energy. So that's the change in heat minus the work done. So in the case of ACB, in this case, you get 80 joules of work and, 80 joules of heat and 30 joules of work. So you in total get 50 joules positive of internal energy change. And this number is path independent. So it doesn't matter which way you take, you should get the change of internal energy to be 50 joules. So use this as a way to fix the conditions to work out what the work or the heat along other paths should be. So for example, in part 1, you're now looking at ADB and saying that the work done by the gas is 10 joules. So done by the gas, so positive 10 joules. And you need to find out how much heat flows into the system. Done by the gas, not to the gas. So this is actually minus 10 joules. Yep. Oh, no, I don't know what I'm saying. Ignore me. If done by the gas, it's positive 10 joules. So, okay, so now your delta U equals delta Q minus delta W. You want to find delta Q, you know these two, they just rearrange to get delta Q is equal to delta U plus delta W. So you got 50 joules of internal energy change, that has to be the same, and plus 10 joules of work done. So altogether, you should have 60 joules of heat flow into the system along this path. All good? Okay, and for the next part, is that when the system returns from B back to A, but now goes along the curved path instead, the work done on the system is 20 joules. So for this part, now your delta U, you're going from A to B, you gain 50 joules of internal energy. So when you come back, you should give back into 50 joules. So going reverse, you get negative 50 joules of internal energy. Yeah. And this time you have work done on the system. So your delta W is a negative number. So it's negative 20 joules. So yeah, work done on the system is negative the work done by the system.
And yeah, and now you can just work out. So delta Q is equal to delta U plus delta W. So in this case, it's minus 50 joules, minus 20 joules. So altogether, you got negative 70 joules of heat flowing out of the system. So this is heat loss. Yeah, and finally, if UA is equal to 0 and UD is equal to 0, so UA here is equal to 0 joules, and UD here is equal to 0 joules. Find the heat absorbed in the process AD and DB. Oh, yeah, right. Yeah, sorry. There's a big statement in front of 0. Oh, okay, I hope I did this question right. Oh, no, I think, yeah, it's fine. All right, so for the third part. So you want to work out the heat going from here to here to here to here. So you first want to work out the work going from A to D, because you know the changing internal energy in this case. So this is actually the same as the work going from A to D and then all the way to B at the end. Because at the last one, you're staying at a constant volume. So here, dV is equal to 0. So you don't do any work on the last leg of this trip. So you only do, all the work must be done on in this first process. So delta U of A to D is equal to the heat flow from A to D and minus the work going from A to D. So then Q flowing from A to D is delta U, A to D, plus work A to D. But instead here we just replace this from A to B because it's the same amount of work. And we worked that out before, so that was the work done here. So this is 10 joules. So going from all the way from A to B by this path, you do 10 joules of work. So here you get 40 joules of internal energy change going from A to D, plus the 10 joules of work done on the first path, but then we just cheated and used the entire path. So altogether, you get 50 joules of heat flowing into the system. Yep. And also, you know that the total path going from A to D to B gets a 60 joules of heat flowing in. So if I got 50 in the first part and I only got one more leg to go, then the remaining 10 must be all going into here. So 10 joules of heat flowing in, because that's just how much we have left, and it has to add up. Yeah, any questions? All good so far? Okay. So then for the next question, so question 5 is like a whole list of processes that you have to do. I'm not going to do all of them because I don't have enough time. And also, it's actually good to keep some of these for practice when you want to study for exams. And the process to do them is the same every time. So if I show you like some of them, you should be able to just figure it out for the rest. So, 3 of the nasty-ish ones to do, and then you can try the rest later at home. I mean, if you give up, the answers are also unmovable. So. Okay, so the first one I'll do is the Stirling engine. Stirling engine or Stirling cycle, whatever you call it. Okay, so draw the PV diagram first. So here you have two isovolumetric processes connected by two isothermal processes. And let's just call this A, B, C, D. And it goes around this way. Yeah, and I'll call this the lower volume and the higher volume. And then the pressures are just going to be labeled with whichever point they correspond to. Alright, so the first, you need to work out a couple of things, but really the work done, heat input and output, these are going to have to be done anyway if you want to derive the efficiency. So the efficiency is the kind of the ultimate goal here. The other two coefficients of performance are similar to efficiency, but they don't need to be put in that specific form in an exam, so you don't have to worry too much about knowing how to derive them. Like once you get the heat in and heat out in the work, then you can just put them together to get whichever coefficient you want. But the efficiency is the one that we really want right now. And it's defined as 1 minus Q out divided by Q in. So really you want to work out the Q out and the Q in for the particular system. Or alternatively, I think there's another. I think it's also Q in divided by the work done. Subject to change. Okay, so now let's just try to find out what these two are so we can get eta. So first, let's do the easy ones, going from the two easy ones are the two isovolumetric processes because dV is equal to 0, so no work is done there. So work from A to B and work from C to D are both 0. And now what's left is to find the work done on two isotherms. So this one, let's call the hot one and the cold one. And yeah, so you've seen how to do work going from isotherms. It's just using the ideal gas law to get the temperature out. So D to A, that's the hot isotherm, the TH. And then integrate from VD to VA of dV on V. And you get nRTH log of VA on VD. Oh, sorry, I shouldn't call VA VD. It's VH and VL. Okay, and VH is larger than VL, so we know this is a positive work. And exactly the same for work going from B to C. You don't have to work out, you can just put in nRT, but it's a cool bath. This one's a TC, and log of VL over VH, because you're going the other way. So this is less than 0, so there's a work getting done on the gas. Okay, and now you can start going look at the heat. So on isotherms, the internal energy is constant because internal energy has one definition where you have CV and RT. So in this case, all of these are constants. If your T is constant, then your internal energy must also be constant. Yeah. Yeah, I think it's like within how you define this capital R and this CV. So, Yeah, I'll say so. I don't know. I can't remember for sure, but it sounds like one of those. From the equipartition theorem, yeah. Yeah, I don't remember all the formulas, to be honest. But yeah, but anyway, you can see that if t is constant, doesn't matter what you write in front of it, has to be constant. So, okay. Then, in this case, du on the outer terms is equal to 0, and that's equal to d cubed minus dw. So if we know that's 0, then we can work, equate these two. So d cubed is equal to dw. So the heat transfer going from D to A is just equal to the work done from D to A. So we can just take that expression directly. So I'm going to write it out again. And same for Q going from B to C. That's going to be equal to the work done from B to C. And that's just going to equal to that. Yep. And now the next part is working out the isochloric process. So on the isochloric, du is equal to d cubed because dw is equal to 0 in this case. So if we can work out what the change in internal energy is, we should be able to work out what the heat flow is. And for in this case, so Q going from, let's see, go from C to D first, is equal to integral of du. And it's an ideal gas. So you remember that you have the U is equal to 1 over gamma minus 1 nRT. So you can put that in here. So this will be nR on 1 minus gamma, integral from Tc to Th dt. And this is just a trivial integral, so you just get nR over 1 minus gamma of Th minus Tc. Yeah, and this is the exact same process for going from A to B, except rather than going from Tc to Th, you're going from Th down to Tc, so this gets swapped. But the rest of these remain the same because of the same gas. So it's still nR on 1 minus gamma, Tc minus Th. And this is obviously positive, and this will be negative, so heat flow in and heat flow out. Okay, I knew I got this wrong way around. It's W on Q in. Kind of running out of room here. I'm going to move the other board then. Okay, now to finally derive the efficiency, you take the total work done in the entire cycle and then divide by the amount of heat that's flowing in. So the total work done around the cycle is just the sum of the two work going from A to B and D to A. So that was nR Th minus Tc times log of Vh on Vl. So all I did was I flipped one of the logs for VL and VH, so I picked up the negative sign in front so they could both have log of VH on VL, and then took out the common term, and that's how I got the TH minus TC. Okay, so that's the work around the cycle. So eta will equal nR TH minus TC log of VH on VL divided by the work in. So divided by the heat in. So for the heat in, you have to look for the positive ones. So the negative ones are the heat out, and we don't want them for this calculation. So only for the heat from C to D. So we first have the nR on 1 minus gamma, Th minus Tc. And then the other heat in will be the one that's positive work. So it's the heat from D to A. So that's plus nR Th log of VH on VL. The other heat terms are heat loss terms, so we ignore them. So now you just have to algebraically massage this into the form that they gave you into, in the table to get this. In an exam, they actually will ask you to do this. So it's one of those things that once you've seen it once, you know how to do it. So better to like kind of try this for all the cycles at least once. So the first thing to do is to cancel out all of the NRs, because you got one in each term. And then also divide the whole thing through by log of VH on VL. So you end up picking up an extra log term here, but you get rid of these two. So you get TH minus TC divided by NR 1 minus gamma TH minus TC divided by log of VH on VL plus TH. And then take out one TH from each of the terms and cancel them out. So this will equal 1 minus TC on TH divided by NR 1 minus gamma 1 minus TC on TH. And this is just TH, so just plus 1. I think in the formula, 1's out the front, but it's still the same thing. Yeah, and okay, you haven't proved this yet because we skipped right into the Stirling cycle. If you do the Carnot cycle, you realize that the efficiency for the Carnot cycle is 1 minus TC on TH. So then you can sub that in for these two. So you get the efficiency of the Carnot cycle divided by 1 plus, I should have died 8. And yeah, so that's the efficiency for the Stirling cycle. I don't think there's anything sinister physically happening. It's just a lot of algebra at the end that you have to just know to sum in those things. Otherwise, you can sit there and work it out, but you don't want to waste this time in the exam. Any questions about this? No. All right, probably have time to do one more. Let's do the diesel one because that one's a bit annoying. So it's best someone show it to me first time. Okay, so for the diesel cycle, not quite sure why it's called diesel cycle. I think it's because it's compression kind of ignition. But anyway, not an engineer. PV, you get one isobaric process and then 2 adiabats connecting to an isochoric process. And it goes this way. This time I'm going to call it 1, 2, 3, 4. Yeah, okay, nothing really special about it. So let's just work through it. So first, from process from 1 to 2, we want to find the work. So always start with the work. So work is equal to PdV. But these are isentropic lines or adiabatic lines. So PV to the gamma is equal to some constant. So I'm gonna just sub in that to get the constant times by integral from, just call these V1 and V2, dV on V to the gamma. And that's equal to C V to the 1 minus gamma divided by 1 minus gamma, V1 to V2. Yeah, and the exact same way that we did before. So you get 1 over 1 minus gamma on the front, but then you get V2 and divide by V2 gamma, so you get V2 C on V gamma plus or minus V1 C on V1 gamma. And then using these two to sub back in your pressure for that particular point to make it easier. So this is equal to 1 over 1 minus gamma, P2 V2 minus P1 V1. So that's the work going from 1 to 2. And you do the exact same thing for work going from 3 to 4 because that's also an adiabat. So the work from 3 to 4 is equal to 1 minus gamma, P4 V4 minus P3 V3. Yep. And the process on 4 to 1, that one's also caloric, so your volume doesn't change, so no work done here. This one is at constant pressure, so in this formula, it's just a trivial expression. You get work from 2 to 3 is just P2 times V3 minus V2. So that one's free because it's a flat line in your pressure. Okay, so now you got all the work in the entire thing, so you can work out the work over the entire cycle. And that's just the sum of all of them together. So in this case, you get 1 over 1 minus gamma, P2 V2, okay, it looks really ugly, but you can simplify it slightly because you can see that P2 and P3 are the same thing. So I could sub in P2 for this P3. So this could be labeled as P2. So now I got a P2 V3 and a P2 V3 here, and I could collect those like terms. And I got another P2 V2 and a P2 V2 here. So I could essentially combine these together to make it slightly less gross, but still pretty gross. So you get P4 V4 minus P1 V1 plus gamma to the 1 minus gamma, P2 V2 minus P2 V3. So this is the work around the entire cycle. Oh, sorry, I forgot to rotate this one. Okay, and then going, and then now you have to work out the heat. So the same thing before, so heat going from somewhere is always going to be the changing internal energy plus the amount of work done. So using this, we first work out the heat from the changing internal energy from 2 to 3. So going from the easy one, the isobaric process first. So from 2 to 3, from isobaric process, you know this is just 1 over 1 minus gamma minus 1 times P2 or P3, depending on which one you want to label. But I think we replace all P3s with P2s up here, so best to keep it consistent. And then the delta V, which is just V3 minus V2, because everything else is constant. So then, therefore, the heat flow from process 2 to 3 is equal to 1 over gamma minus 1, P2 V3 minus V2, plus P2 V3 minus V2. So this just adds another factor of gamma here, and you can forget about this term. So that's the total heat flow into process 2 to 3. And then you can do similar things to process 4 to 1, except it's even easier because for process 4 to 1, your W is 0. So when you work out the internal energy change, it's just immediately the heat change. So for 4 to 1, delta U 4 to 1 is equal to 1 over gamma minus 1 P1 V1 minus P4 V4. And that's also equal to the heat from 4 to 1. And because P4 is technically equal to P1, you can take this out as a common factor. P1 out here. Okay. And then you don't have to work out the heat for the other adiabats because they don't have heat exchange in adiabatic processes. I'm going to have to delete that. Okay, and now for the efficiency. So the efficiency, this time we're going to use 1 minus Q out divided by Q in. So we forget about 1 for now. Let's just work out this. So in this case, Q out is 4 to 1 because the V1 is less than V1's I did this one right. No, I didn't. Sorry, I wrote that part wrong. V4 is equal to V1. This is actually V1, P4 minus P1. Yeah, so this is Q4 to 1 divided by Q2 to 3. So okay, that's oh god, I wrote it. Okay, so the 1 and 4 the other way around. I'm not changing it again. My bad. So that's V1 1 over gamma minus 1 V1 P1 minus P4 divided by gamma minus 1 P2 V3 minus V2. So that's just equal to V1 gamma P2 minus V2. Okay, and now if you look at the final expression, they don't actually have pressures in the final expression at all. They're all volumes. So you know, as soon as you see that, you should know that you need to use the PV gamma equals constant to sub out all of the pressure terms. So in this case, along our two adiabats, we got P1 V1 gamma is equal to P2 V2 gamma, and then P4 V4 gamma is equal to P3 V3 gamma. So use this to sub out the P1 and P4. So you get V1 P2 V2 gamma divided by V1 gamma minus P3 V3 gamma divided by V2 gamma divided by gamma P2 V3 minus V2. Okay, P3 is the same as P2. So these two can come out the front and cancel out with this P2. So these all go away. So yeah, just gonna rub that out, and that, and that. And now you just have to stare at the final expression and figure out to do exactly these steps. So take out one factor of V2, take out one factor of V2 from down here. So you get V1 on V2, 1 divided by gamma, V2 gamma on V1 gamma minus V3 gamma on V2 gamma divided by V3 divided by V2 minus 1. So that's your alpha minus 1. So you got that sorted. Now this is your R, and you need to take out a V2 divided by V1 all to the power gamma from this entire bracket. So you get V1 on V2 times by V2 divided by V1 to the gamma. And in the denominator, you go 1 minus V3 gamma, V1 gamma, V2 gamma, V1 gamma, divided by alpha minus 1. I'm just subbing alpha now. And then these two cancel out. So you end up with, and this is like the inverse with this -1. So this is equal to V1 divided by V2 to the power of 1 minus gamma times 1 minus V3 over V2 all to the gamma divided by alpha minus 1. And you can sub alpha into there and R into there, and that should be your efficiency. Or once you put it back in 1 minus at the front. Yeah, that should be all. Yes, that's 1 minus alpha to the gamma divided by R to the gamma minus 1 times alpha minus 1. Yeah, and you absolute value of the whole thing. So I think in the answer it's alpha to gamma minus 1, but because you take the absolute value of Q out and Q in, so the sign here doesn't really matter. Okay, any questions? Well, okay, if not, then that's it for this week. And we'll go through the rest of the questions in problem set 2 once you covered Maxwell's equations or relations in the lectures. Okay. Yeah.